Hey, welcome back, everybody. In the meanwhile, the speakers are trying to log in, but we have a few speakers already on the line. That brings me to, well, first some other things like a poll or whatever. We're going to talk about the future focus, especially concerning the weather. And the next session will show how EUMETSAT is shaping the future for weather forecasting. EUMETSAT next generation of satellites, they will deliver data faster and higher resolution, thus empowering weather forecasters and climate scientists with unprecedented tools and information. But what kind of information do we need? Well, please go to the poll. You have three, chat, questions and poll. Go to the poll. If you go to the poll, you can see some options, and one of the options is what kind of extreme weather events do you monitor or experience most often in your area? And it's a pretty long list, so take a look. Is it tornado, clouds, strong winds, hail, or is it hurricane or cyclone with strong wind, heavy rain? Or is it blizzard, heavy snow, ice, cold temperatures? Or is it dust storm with strong winds and arid conditions? Or is it flood, heavy rainfall? Or hailstorms, cold and warm temperatures, rain, ice? Or ice storm with freezing rain? Well, I suspect it's not happening that often, although it gives very nice images. But please fill in the poll what suits best for you, and it'll take some time until everybody filled it in. But you can see the results on later. Feel free to ask questions to the speakers during the session at the button questions. And I can ask the question afterwards. We first like to introduce Ellen Björk Jonasdottir. Dottir, I understand, is Icelandic for daughter, so she's the daughter of Jonas. And she lives in a beautiful country, Iceland. It's only 370,000 inhabitants. The Netherlands got 17 million. And the area is 2.5 times bigger than the Netherlands, or 1/6 of France. So it's a big area with a few people, so they have all the space. As one of the few countries where fire and ice can exist next to each other. How cool is that? I would really, if there was no COVID, I was already gone to Iceland to watch the eruption, which is going on right away. But they also use the natural power for sustainable energy, and that's great. Ellen lives in Reykjavik, where 2/3 of the Icelandic people lives, and she likes the outdoor life. And I asked her, where can I wake you up for in the middle of the night? She says, well, adventure or an eruption. And today, June 17th, is a national day, so a public holiday in Iceland. They celebrate the fact that Iceland became a republic on 7th of June in 1944. So actually, she's got a day off, but she still wants to be here. So we're extra happy that she could join us. And to be sure that the connection at home is still fine, Ellen pre-recorded her story and is going to tell us her view on how satellite data are valuable for Iceland. The video.
Good morning. My name is Elín Björk Jónasdóttir, and I am the head of weather services at the Icelandic Meteorological Office. And I also work as an evening broadcasting meteorologist for the National Public Radio here in Iceland. I'm going to briefly introduce to you how we use satellite imagery in communicating weather and warnings and even some other natural hazards that we have to deal with here in Iceland. I called this little talk The View of Iceland from Space. And one of the things that is important to notice is the location of our island here in the middle of the North Atlantic. Iceland is located close to the Arctic Circle. We are very far north, and as you can see, the southern point of Iceland is further north than both the southern points of Greenland and Scandinavia. So having a country this far north means that we are on the polar front. We have quite severe winter weather in Iceland, and we also have the possibility of deep lows all year round. The ocean plays a large part in the dynamics of our weather, so we have to monitor the ocean fairly well. And we have this problem, this minor issue of being so far north that Iceland is not at a good viewing point for geostationary satellites, at least not for small-scale phenomena such as fog or even small fires, forest fires or bushfires. We don't see small cells of afternoon showers on the geostationary satellites, but what we do see, however, are the large-scale phenomena in and around of Iceland. And as I've said, the severe instruments that are on the geostationary satellites make for fairly fuzzy images of Iceland itself. But as you can see from this image, which is our view from Severi, that we do see all of the North Atlantic and a large part of Europe here. And when you're not looking only at details or small-scale phenomena, but also larger-scale phenomena, which could have implications in a wider scope than what we have here in Iceland, this is a very good view to have. Now, this loop that you are looking at is from the infamous 2010 Eyjafjallajökull eruption. And of course, that was not just the private business of Icelanders, because the ash did go all the way to Europe and halt flights for a few days. And this was our main way of monitoring where the ash was actually going. In this case, the ash went around a high pressure system south of Iceland and actually backed right into Iceland and the international airports once it had gone really, really far south. And this imagery actually helped us warn for an ash cloud coming over the international airport and into the Icelandic airspace, which is marked with the red lines here. So imagery, even though it's fuzzy and maybe not the prettiest of pictures, can really be helpful for us to look at the large-scale phenomena that we have to monitor. For broadcasts, polar orbiting satellites provide a much better view of Iceland because, of course, it has a much higher spatial resolution, but the temporal resolution is not as good as the Severi. So then we just have much less frequent observations, and we can't show loops or movement of anything with polar orbiting satellites, but we can, however, monitor things in quite a detail. So from this particular image, for example, we were looking at the front from the low that we can see close to the east coast of Greenland. We also use it to monitor, for example, sea ice. And on clear days, we can see incredible details. We can see snow cover in mountains. We could see fog in specific valleys or even at specific airports. And so these are very useful for us, even though the temporal resolution is not great. That's fine. Again, for the Severi or the sort of high temporal resolution imagery that have a low spatial resolution, in December of 2019, we saw our first red weather warning. It had to be pretty bad for us to go to red, but we did in December of 2019. And the models did a fairly good job of modeling the weather that we were expecting. However, we could see that there were eddies on the inner edges of the frontal system along the east coast that kept forming in a sporadic way from one run to the next in the high resolution models. And we knew that those were going to have a large effect on exactly how bad the weather would be in North and East Iceland. And so our only option to actually forecast these events well was to use satellite imagery. And in this case, the black arrow points towards one of those eddies, and it could show us how close to the shore this eddy would be. And so we were able to actually confirm that one of the models were right, the one that we had actually sort of banked on and used as our main model. And we were able to talk to civil protection and search and rescue and the police in these areas and say, okay, this weather is actually going to materialize, please be aware. And then we could sort of issue the red warning and be pretty sure that it would actually materialize. We don't just use satellite imagery for weather. The Icelandic Meteorological Office is actually a multi-hazard operation, so we monitor hydrological events, geophysical events, including earthquakes and volcanoes. And on March 19th this year, we had an eruption start in the southwest, in the Reykjanes Peninsula, very close to both the capital of Reykjavik and the international airport. In the previous weeks, we had thousands of earthquakes in the area, and INSAR images from the Sentinel satellites actually had shown us where the inflation of the ground was happening and where the magma was accumulating. And so we had a pretty good idea of where exactly the volcanic eruption would come up if there was a fissure opening. And that turned out to be really well sort of examined by the satellites and by the geophysicists who used the satellite imagery to look at these things. And then once the eruption actually started, on a Friday evening, on the 19th of March, we could actually use, again, the CVRI, even though there is a fairly low spatial resolution, we could use the CVRI image to actually confirm that there was an existence of an eruption. And all we needed was this one little black dot here. You can see in the Reykjanes Peninsula that something here is much warmer than the surrounding low stratus clouds. And with that, we were able to confirm that there was an eruption because it fitted all of the other data that we had. And you can see it here where the arrow is pointing. And then later on in the evening, we got a polar satellite imagery from the METOP-A, and that showed exactly the same thing. And so here we were actually able to use satellite imagery both for the geophysical monitoring and also for the atmospheric monitoring. And here you can see an image of the crater that's formed now. This has been an ever-changing eruption, and we still use satellites to monitor it, both for the atmosphere and for the geophysics. And we hope to use satellite imagery more in the future. We have ongoing development work to use what is available to us now, and then we hope that with increase in polar orbiting satellites and even maybe an Arctic latitude geostationary satellite at some point, that would be nice, then we would enhance our chances to use satellite imagery for nowcasting and warnings in all of our natural hazard monitoring.
Oh, Ellen, if I watch that presentation, I think I want to go to Iceland right away. What I'm doing here in the Netherlands. I've been to Iceland though a few years ago, and they said, well, if you don't like the weather, just wait for 5 minutes.
Yeah.
So I can imagine that in Iceland, because it's so much north, that you're just a lack of good information. It's ocean all around you. Are there specific satellite products that work better than others for you because you're so north?
Yeah, so what happens in the north is that you lose daylight in the winter time. So as the days get shorter, we lose more and more light. And so the infrared spectrum, the infrared images are really, really important, and the radar images. So with all the new satellites having radar capabilities and things like that, that has really been kind of a revolution, I think, for us. And also with the sort of new like the SAF image, the OCSAF, where you can see, you know, the wind speeds over the ocean, things like that. That was a huge help because we didn't have enough information from the ocean. So yeah, so satellite imagery is really important.
And are you working together with other institutes if it goes to interpretation of the satellites?
Yeah, so we have a small sort of satellite or remote sensing department at IMO, but then the University of Iceland and also the Icelandic Land Survey have experts, and they especially join in when we do the geophysical monitoring, of which I showed an image. So we don't have any other weather experts, so that's basically just the Met Office, but for everything else, like sea ice and the land deformation, we do collaborations with those institutes.
And I can imagine with those eruptions, you know, living nearby in Reykjavik, that also air quality is very important. How do you warn the people for the air quality?
So we have we are running a few models, air quality models, specifically designed to mimic eruption air quality. So it's sulfur dioxide mostly that we're looking at. And we've put up a lot of ground sensors, but we also use satellites for that. So one of the Sentinels has a SO2 monitoring capability, at least. So we are using that. And then we have others who are the ocean monitoring satellites, and they work for SO2 as well. So that's a big part of our work now too.
Well, and we're officially guessed by EUMETSAT. What would your request to EUMETSAT? What would be the greatest thing they should do so you can work things out much better for your country? You can do a request right away.
Well, you know, the best thing ever would be a geostationary satellite that's closer to my sort of geographical location than the equator. So if you can figure that one out, to have a far north geostationary satellite, then that would make us really, really happy.
Yeah, a better network permanently hanging over.
Yeah.
Yeah.
Yeah, because it's very fuzzy. We're very far north, so the angle is pretty bad from the current geostationary satellites. So
yeah.
We might be defying physics to trying to do it though, so we'll see.
Well, you never know. What's your dream for 2030? Your ultimate dream?
Yeah, so more polar orbiting or a geostationary satellite that sees better what we are doing, what's happening around us. But we're very excited for the new generation of both polar orbiting and geostationary satellites. I think it'll bring us a lot of new information and be a lot of help. So we are very excited for all of the new things coming from EUMETSAT.
Great. Well, Ellen, thank you so far. And well, hope you're still watching the rest of the sessions. And if not, have a very nice holiday time.
Thank you.
And thank you so much for your input. Thank you very much. We're going back to another poll number 2. You can go to the swap card tool again. You know, you've got 3 buttons. Yeah, I say buttons. You can go to the poll. And what I would like to know, do you think the general public understands the uncertainty of weather forecasts? Well, answer yes or no. That's going to be a quick one. And I can imagine that it's difficult to say yes or no, because uncertainty says a lot. So fill in the poll and I will look later what you just answered. And I can go to the next presentation of Tony McNally. He joined the ECMWF from the Oxford University in 1989. He's still living on Oxford, and he says it's a great energy, great atmosphere for science innovation. And in his spare time, he likes enjoying the weather, even the British weather. Okay. And besides that, he likes sailing, windsurfing, and skiing. And I asked him, what can I wake you up for in the middle of the night? And he says, well, if you've got a really good idea, yeah. But I can also wake up and then worrying about everything that might be a bad idea. So let him sleep. And I asked this question to all the speakers because you can see on their CV, what are they doing? Where are they working? But I always would like to know, what is that person? What do they in the spare time? What's the person like? And he also got a dream for the world, its leaders, scientists and people to have a better plan of how to protect this beautiful Earth. Well, before that, we need scientists, Tony McNally. We need scientists. Tell us more about the interaction of satellite data and global weather forecasting, please.
Good morning, Helga. Thank you for the introduction. Can you hear me okay? I guess the answer is yes.
The answer is yes.
Okay, well, thank you for the wonderful introduction, and thank you to the organizers for inviting me and giving me a chance to speak to this audience. I'm going to spend 10 or 15 minutes talking about satellite observations and global weather forecasting. Obviously, I'm not going to be talking about everything, but I'm going to try and limit it to a few maybe quite interesting and exciting aspects of what we do at ECMWF. I'm just going to quickly spend 2 minutes telling you what ECMWF is. Not everybody knows. Who are we? What do we do? We do numerical weather prediction. And I'm going to then talk more about using satellites for global weather forecasting, but then one particular very exciting, very important, very close to my heart aspect, and that is the forecasting of severe weather, tropical cyclones and hurricanes. But before we get going, I'm going to ask 2 questions of my own, Helga. It's not just you that gets to ask the questions, and you can put your answers in the chat as well. First of all, look at this beautiful view of our planet. Look at the amazing sort of structures. If you get this sort of, you see the clouds racing across the mid-latitude. You can see convection bubbling up in the tropics. You can see the sun heating the Earth as the Earth rotates. But what gives us, what could possibly give us that view of the Earth? So please put your answer in the chat if you think you know the answer. And the second one, this is a little bit more interesting. I don't know if any of you got political aspirations, but just imagine it's October 2012 and you've just been elected the mayor of New York City. Congratulations, by the way, it's a great job. The telephone rings day one and you're told that a super hurricane is about to hit your city in 5 days' time. And the scientists are telling you, you must evacuate Manhattan immediately. Manhattan, not Reading, not DeBilt, not you need to evacuate Manhattan. And you look out of the window, it's a beautiful autumn day. What is your first question? What's your first? Put your first question in the chat as well. So on with the talk. Who are we? What do we do? Who are we? We are an international organization, intergovernmental operational forecasting and research. We have 34, soon to be 35 cooperating and member states, about 350 staff, and these staff come from many, many different countries. It's an incredible place to work and an incredibly international environment. What do we do? This is what we do. Our primary activities: numerical weather prediction. We do weather forecasting. We do hours, days. We extend out into monthly weather forecasting and even seasonal forecasting. Seasonal forecasting being defined around the sort of 6-month range. We do monitoring, environmental monitoring and prediction. Anything that affects you, we monitor it. So the weather, but also air quality, fires, floods, any threat or any disruption to human activity, we monitor it. We do production of what we call reanalyses. They are historical views of the old planet's atmosphere, and that helps our climatologists. It tells them what has happened. And of course, we offer a supercomputing facility and a training program. But this is our main thing. This is our lifeblood. We forecast the weather. We are fortune tellers, if you like. We try to say what's going to happen in advance. So my first question, I don't know what you thought gave us this beautiful view of the planet. If you thought it was a satellite, well, you were wrong. And this view was not produced by one of these at all. It was actually produced by one of these. This is our supercomputer based in the UK in Berkshire, but will soon be moved to Bologna in Italy. And the image that you're seeing on the right-hand side of the screen is a pure simulation. It's not real at all. It's what our computer model makes a simulated atmosphere. It tries to make a copy or a digital twin of the real atmosphere. And I hope you agree, it does look like the real atmosphere. And if you don't believe me, I'll show you in a moment just how close it really is. But what's inside this computer? What is inside this big box that sits in Berkshire? Well, we have our numerical weather prediction system, and the numerical weather prediction has 2 components. The first component is called data assimilation, and what it tries to do is say, what is the atmosphere doing right now everywhere in the globe? And of course, to answer that question, we really need observations. And the primary source of observations for global weather forecasting is satellites. Satellites are the only observing system that can tell us about the weather everywhere, in the middle of the Atlantic, in the southern oceans, in the central Pacific. They're the only observing system that can do this. And then once we know what the state of the atmosphere is right now, we use our knowledge of the physics of the atmosphere, the numerics of the atmosphere, the physical parameterizations, radiation, friction, everything we think we know about how our atmosphere works, we encapsulate that in a numerical model. A numerical model that works on a grid structure. This grid is approximately 9 kilometers apart and it spreads over the whole globe. And we try to model the evolution in time of this initial state, taking into account the physics and, of course, the physics of things like the ocean, which are an integral part of how our atmosphere evolves. And what does the output look like? Well, I've shown you that, but here's a zoom. And if you didn't think that the simulation that I showed you was particularly realistic, this is a real satellite view now, put side by side with a simulation, a pure simulation from our forecast model. And you can see that there's a pretty good correspondence. Of course, if you stare very long and very hard at this, you'll see differences. And we are not perfect. The simulation is not perfect, but it's pretty good. And what I really want you to take away from this image is just how detailed our model is. People think of global forecasting models as big floppy things that just don't really give you any detail. Look at the detail in the simulation. I even though it's somewhere where I work, I find it pretty impressive and awe-inspiring. So satellites, that's what we're here to find out, and satellites for forecasts of hurricanes and tropical cyclones and severe weather. Why does it matter? Well, you see a lot of these images in the press and you see them on websites, and this is Hurricane Dorian, and it's Hurricane Dorian viewed from the Sentinel-3 satellite. But this is Hurricane Dorian viewed from the Bahamas. This is real weather. This is the sort of weather that takes human lives. It's absolutely devastating. I think most of us who live in Europe, we're so lucky. We cannot imagine how ferocious these weather systems can be and just how terrifying it must be to be involved in the center of one of these things. And if anyone in the audience does know what that's like, I'd really be keen to hear about their actual experiences. This event in the Bahamas was devastating. Dorian sat on the Bahamas for nearly 24 hours, and yet only a handful of people actually lost their lives. It was an extraordinary success in both weather forecasting. It was very accurately forecast, but also the actions that the decision makers took were extraordinarily good, and they saved literally tens, possibly hundreds of thousands of lives. But we cannot get complacent. Even in modern history, these storms kill people. And the worst example of that is back in 2008, where Typhoon Nargis killed nearly 130,000 people. So this matters. This is not whether I'm having a barbecue this weekend. This weather really, really matters. The key aspects for forecasting a hurricane successfully is we need to identify what we call the genesis of the storm. We need to know when it first appears on the planet. Of course, if we don't know it's there, then we can't track it and we can't predict it. So we need to capture the genesis. Then we need to have a knowledge of what we call a large-scale steering flow. The steering flow is what pushes this storm from where it is born to where it hits. Now, typically, if you look at the Atlantic, the steering flow is from the east to the west. And that is driven by the large-scale weather patterns. It's not driven by the storm itself. It's driven by the flow in which the storm sits. And then, of course, we need to model the physical processes that lead to things called rapid intensification. Why does a storm go from category 3 to category 5 overnight? Or why does it go from 5 to 1 in a matter of hours? We need to model that. And satellites are critically involved in all of the above understanding. Early identification, the genesis. This is an area off the west coast of Africa, and pretty much every storm that you will see in the media hitting the Caribbean and the US will be born here. It'll be born in this red box. This is around the Cape Verde Islands. And it is a combination of waves that come off Africa and the local ocean conditions and the humidity conditions means that this is an area where storms are born. And we have very good observing systems for this area. So, why can't we see them? Well, what we need to see is not just clouds. We need to know things like the ocean temperature. Is the ocean warm enough to generate the storm? Is the mid-level humidity right for the storm? Humidity in tropical storms is like fuel. It's like petrol. It is the fuel for the storm. And the one thing that can make a storm shut down is something called wind shear. Wind shear is when the winds at different levels chop the storm like a salami and break it down into different pieces. So there's a storm in here. Can you see it? No, of course, it's difficult to see. Even though we have amazing observing systems like satellites, it's difficult to see these storms. There's so much going on. Of course, you can see the clouds, but there's other stuff in there. There's dust, there's humidity, there's a process called sun glint. So it's a really difficult job, even with our advanced weather systems, to spot the genesis of these horrible storms. And the advantage we have is that the satellites that are flying at the moment can measure in different frequencies. We have microwave, we have visible, infrared, we have radar scatterometers, and the combination of these different views allows us to identify the storm. This is an example of, again, Hurricane Dorian. Now, the marker and the thing in the animation is just a marker for the storm. It's vorticity. Don't worry about what vorticity is. It just shows where the storm is born and where it goes to. But as an example of what would happen if we did not have satellites, of course we have satellites, but what if we didn't? And we sort of take it for granted. What we did is we reran our numerical forecasting system, but we deliberately took away all the satellites. And when we do that, you can see that we don't have observations of these key things out in the ocean, in these remote oceans. And in this particular case, we did not pick up Hurricane Dorian. It just didn't exist. So the really scary, chilling thought is, without satellites, we could give those people in the Caribbean islands almost zero warning that this storm was about to devastate their homes. So satellites, they're absolutely critical. Finally, odd question, but hopefully some of you have given an answer. You just got a great job and someone tries to spoil your day with this prediction. What the obvious question? I'm sure lots of you have got it. It's, are you sure? Are you sure? I'm not going to evacuate Manhattan unless you are sure. The reason? Well, it's not just inconvenience and looking silly. There have been historical cases where evacuations have cost more lives than the actual storm. Then trying to move people out of an area has actually cost more human lives than the actual storm has caused. So if you're going to do evacuation, you need to do it really well at the right time in the right place. So one of our big frontiers of work, if you like, at ECMWF is trying to capture this idea of uncertainty. You know, Helga, you've already been asking questions about uncertainty. But the way we capture uncertainty in our forecast model is we run it many, many times. We try to adjust the initial conditions to say, well, this is what, but it could be slightly different this way or slightly different that way. And we run the system again and again and again and again. And what that produces is what we call an ensemble of forecasts. In this case, 50 different forecasts of the same storm. And from these 50 different forecasts, we can convert that to what we call a strike probability map. And so if you're the mayor of New York, you can see, or in this case, this is Ireland, you can see, yes, our forecast was predicting a hit on the coast of Ireland, but there's quite a lot of uncertainty at this 5 or 6 day range. So that's what we try to do. But is it sufficient? Well, I don't know. Actually, the answer lies with you guys. You guys are the media, you're the weather presenters, you are the people who interact with the public. But it's really, really difficult. I mean, look at the panel on the left here. This was the strike probability for Hurricane Sandy back in 2012. This is the Mayor of New York scenario. That our main forecast was saying that the storm was going to hit New York, but some of the, what we call the ensemble members, were actually predicting a more normal behavior. So which one do you want to believe? The one or two outliers or the majority that predict destruction? Here's another one. This is Hurricane Irma, hit the media 2017. And the authorities were trying to decide whether to evacuate the east coast of Florida or evacuate the west coast of Florida, or which one would you do? The cone of uncertainty covers the whole of Florida. So an absolute nightmare for our decision makers to work on. Even with what we call the best model in the world and the best way of capturing uncertainty, decision making is really difficult. And this final one about Hurricane Dorian. The US model was predicting that Dorian would smash into the Florida coast. Our model was predicting that it would stall over the Bahamas. If you are the decision maker, which one would you believe? So this is an unsolved problem. We're trying our best, but we were hopefully working with decision makers to try to decide what helps them the most, what is the most useful thing that we can produce. And with that, I will stop talking and leave you with a summary. Thank you for your attention.
So we're reading the summary. Well, thank you, Tony. It's very interesting. A lot of nice images, and I can see in the poll that your work is very, very needed, because we asked the audience, do you think the general public understands the uncertainty of weather forecasts? And 92% says no. So we have a big issue to do, because how can we, if even for us it's uncertainty, it's maybe difficult to feel, are we evacuate, and where are we going to do, and how can we move on with the people? How can we explain it to the people? And if we did it, we did a right prediction, but okay, the weather is not always listening to our prediction. Then we have the issue that it doesn't occur, and then people say, oh, you were wrong all the time, and we're not going to listen the next time. So there are very big challenges ahead. What's likely to be the next big challenge or the big advance in numerical weather prediction for severe weather forecasting for you?
I think the big advance will be that we know that in the range of maybe 3 to 4 to 5 days, our forecasts are really, really accurate, really accurate. And the uncertainty around them is very small. People can rely pretty much on those forecasts. Where it gets a little bit more difficult is that, as you saw in those strike probability maps, beyond day 5, those maps start to broaden, and the scenarios, the possible scenarios, tend to broaden rather dramatically. Now, the problem is that if you're in a large populated area, perhaps 3 to 4 days might not be enough time to make the decisions that you need to make. So our goal, what we're trying to do is we're trying to say, well, this is the skill we have at sort of 3, 4, 5 days.
In the meanwhile, you're trying to get your head back on the screen. That's a good idea. Close the presentation. We like to see you. Pauli Ruti is coming in. Paolo. Is it okay?
Good morning, good day, everybody.
Okay, but Tony, you are still speaking. Tony, I lost you somewhere.
Sorry, can you still hear me, Helga?
I can hear you. Go on.
Okay, my apologies. I thought my sound had disappeared. No, so the challenge for us is that we are trying to say, well, this is the skill that we have at 3, 4, 5 days. Can we push that threshold out much further? Can we push it out to sort of 8, 9, 10 days, or even into 2 weeks? This is the big aim for us, is to push our existing skill as far as we possibly can into the future, and try to work with customers to try to do exactly what you say, is to understand probability, to make their decisions appropriate to what information that we can provide.
And that graphical issues might really help to make it more understandable, I guess.
Yes.
So that's also a challenge for you. And we're talking about satellites today. Which satellites are the most important for severe weather forecasting, which you can use from the ECMWF?
We need them all, Helga. I think in the slide that I showed, where we're using different satellites to operating at different frequencies to understand different aspects of the storm, there's no single satellite or no single satellite system which is the best and is the most important. In our operational computer model at the moment, we use about 60 to 70 different satellite instruments, 60 to 70. And we need every one of them to be in the right place at the right time and measuring with the right sort of frequency and technology and resolution. So there's no single answer. There's no favorite satellite. We know that these things work supremely well together, and that if we take just one component away, sometimes we can have a real problem. So we need everything that's currently flying, and indeed we need the stuff which is planned for the future.
Well, thank you. I'm looking if there are still another questions for everybody at home or at work, somewhere out there. Hi, you can still ask your questions. And if it's not asked in the time that's meant to be asked, we can still afterwards answer the question as well. So feel free to ask your questions. Tony, so far, thank you very much for your contribution. We have also a poll for you at home. Again, maybe you saw it already. The question was already visible. Do you think the general public is as aware as it should be of climate change and its consequences? And this is the reason why we ask this question, because it's connected with the next speaker, which is Pauli Rutti. I hope I pronounced it very well. He's a director general on all scientific aspects of the organization strategy of EUMETSAT. He's chief scientist. He lives in Darmstadt, and he has always photos of his son and daughter on his desk. And what makes him happy? Well, spending time with friends and meeting people. And hey, now we're in good company. He likes good wine. What else? And you can wake him up in the middle of the night if you want to bring him a gift. So he's someone who likes to get gifts. That's very good. Paolo, you're going to tell us something about how satellite data allows us to go beyond weather forecasting. We're curious. Take the floor, Paolo.
Thank you so much, Hel, and good day, everybody around the world. So that was an interesting title they gave me. So I started thinking, what can I tell that could be very interesting for a media audience? So I would like just to focus a bit, first of all, on something from the past. So if I'm asking our friends online, so what is the link? What is linking telegraphs and satellites? And I think we can easily answer this question back to these two pictures. The first one on the left is a weather map that was daily published by the Department of Agriculture in US, and it was collecting all the data around the continent around US, and then started when many years before, when the telegraph was made possible to connect different parts of the country and to exchange this information. And it was an important aspect. And then on the right, you have this first collection of images from one of the first weather satellites. It's not the first one, it's not Tyrus, but one of the following ones. And collecting different pictures from the satellites, you can reproduce what Tony showed from a model perspective. And that was back in 69. And so they have probably two important aspects that we need to remember later on in this presentation. Is a global view. They allow us to see what is happening on a global perspective. And because storms, they have a large scale, and storms, they don't care about borders, national borders. So, and then the other important aspect is communication. So communication is at the base of the foundation of modern weather prediction, and is a foundation of satellite. Because if you want real-time data from the satellite, communication is an important aspect. But let's maybe just a step further and ask ourselves, so what has been the large use of satellite? And in order to give you an idea, this is from the European Space Agency, just show you the evolution of objects in orbits. It's not the perfect indicator, but it gives you an idea of how fast and how growing is the number of satellites, not only Earth observation satellites, here is counting everything. But if you want to zoom down to the Earth observations, and you look from the European Commission, what is the trend of investments in this market in the last 20 years, or 10 years in this case, you can see how fast and how is growing in terms of billion of euros, the investment. And I think this gives you an idea of what is the relevance into the market, what is the relevance for us. But so what is the most widespread use of data, satellite data in general? In this case, the example is from EUMETSAT. This is the latest state of the global climate report from WMO, from the World Meteorological Organization, where you can find a lot of important information year by year. And the last year, 2020, there was a new record on the carbon dioxide, and the new record on temperature. So 2020 was the third warmest on record year. But what this imply for our day-to-day life? And you can see here on the right the increase of sea level rise. And sea level rise matters a lot to the people. You know that the coastal problems and so on. So this is just a measure from the satellites, and on the picture you have one of the last satellites that has been launched last year. It was basically in November when it's been launched this Sentinel-6 satellite measuring is capable to measure the sea level rise change on a global scale, but also on a specific very high resolution scale. And you can see how this trend is growing. And this is because increasing temperature is most of this heat is stored by the ocean. And the ocean, they are expanding, we know. And this is a way to measure. So it's how important are satellites data for our day-to-day life, and especially for vulnerable regions and coastal regions. But this is just to mention that you can get a lot of information on these kind of satellites. You can get information on very detailed specific trends on specific areas of the world. This is a map of the trends. We know that in the last the last period, the trend was around 3.3 millimeter per year. So it's increasing quite fast. And I think the message here is, you see all the labels here, EUMETSAT, NASA, NOAA, ESA, etc. It's the strong international collaboration. This is another important message I would like to convey, that in the satellite community, what it really matters is the international collaboration, and where we can share data and we can get data that could help us to manage problems such as climate change. Okay, that was very nice. So we can monitor what is on the Earth and what is happening, but how we can move from monitoring to action, and how satellite could be important again when we move to the action. So this is a few statements from the Paris Agreement. So a long-term goal, keeping the increase of global average temperature well below 2 degrees. The target is 1.5. And this is the assessment at every 5 years. So the next assessment will be in 2023 and then in 2028. And then you have on the right, on the left side, you have a kind of monitoring done by the Climate Action Tracker, and you can see where we are in terms of pledges. So, and we are a little bit far from the target, and even the optimistic target, but we are trying to improve. But now the question is what the satellite community can do to help the countries to monitor what is happening and to understand about the emissions. So this is just a figure that gives you an idea for one single continent of how much we put into the atmosphere and how does the carbon cycle works. To make a long story short, if you read those numbers, so if you read almost 2,000 teragrams of carbon, what does it mean? What does it mean to a normal normal people? It's around 300 Great Pyramid of Giza that we put into the atmosphere just for one continent emissions. If you count how much we emit in terms of carbon yearly, is around 43 billions of tons, which is around 7,000 Great Pyramid of Giza that we put in our atmosphere. And then you can see how the carbon cycle in reality is much more complex, because it interacts with the vegetation, it interacts with the ocean. So there's a lot of complexity here. And you go down to the vegetation or to the single plants, and then you understand that you need a lot of granularity. You need a lot of information at very detailed level. And this is where we are heading. So this is the new frontier. The carbon cycle from space, and the new frontier is moving from monitoring the CO2 towards the emission, to providing to the countries another instrument to understand the emissions and to monitor the emissions. And this is the new frontier where European Commission, Copernicus, ESA, EUMETSAT, they are working on new satellite missions to monitor at very high resolution, 4 kilometers, 2 times 2 kilometer resolution, to try to detect even small, medium to big industrial plants and to have a full view of the Earth. And this is just to tell us that when you monitor the increase of CO2, of emissions, or of concentration, you are measuring the CO2 in the atmosphere, so the carbon dioxide and other greenhouse gases. And you have a trend, and you have a seasonal variability related to the ocean, to the vegetation. And then you want, first of all, you want to monitor at very high resolution. This is an image from CNES, from France. And the new mission of their carbon satellite will measure down to the level of details of Paris. Then we will use this information to use the models Tony previously shown to make a kind of reverse engineering and to move from CO2 concentration to emissions. And this is the new frontier where we are moving from measuring the CO2 and other greenhouse gases and combining these measurements. This gives you an idea just of what kind of satellites we are working with, and bringing together different measurements from other satellites. So there will be this carbon mission from the European Commission, which is a joint venture, and where this integration of this observation and with the models will provide us with emissions, and together with other data that we will have from our geostationary and polar system at EUMETSAT with other air quality measurements, will provide a full picture of the problem. And this is, as you can see here, you can see also the last two steps, which is AI and machine learning and policy and technology. And this is back to my first slide, where I was talking about telegraphs and satellites. So we are close to the new era, where probably there will be new instrument that will allow us to connect all this data, and we will have a kind of a carbon weather in the future. So our media friends that we are listening to us, they will probably in the future, maybe in 5, 7 years, not only to speak about what about rainfall tomorrow, but what about CO2 emission or other greenhouse gas emission? That will probably make a big step forward and make us understanding the relevance of what we are doing to our planet. Thanks to everybody.
Thank you, Paolo. I see a remark that the WMO is missing you. Greetings from Klaar. So, and I see also questions coming in to Tony. So Tony, if you look at the question map, maybe you can answer them right away so we don't have to discuss it publicly. And I also have a very interesting question about the legal consequences of a bad weather forecast. Yeah, maybe that's different in different part of the world, but I can imagine that's also very interesting to think about. Is this something that you think about at EUMETSAT, Paolo, about legal consequences of what you bring to the audience?
I think there's we are on the upstream side of the weather prediction, but at the same time, geostationary data are used for nowcasting, for instance. And so what we care from EUMETSAT is to give the most reliable information to our customer and users, especially the EUMETSAT members. So the legal aspects, of course, they are downstream. They are at national level because each nation has a legal framework. But this is extremely important question. And I think what we can say is that the more reliable the information we provide from satellite data and from a weather prediction system, as Tony also shown, I think that's the most effective way we can support the members, and then they can deal with the legal aspects.
Yeah, because if the satellites doesn't work properly and you miss an extreme weather event, if it's going to nowcasting, for example, heavy thundery showers or tornado showers, then you have an issue. But you can't get blamed for it, right? They can't say to you, Paolo, what did you do? We have bad weather, we have unfortunately some people suffering from it. It's your fault, you should have sent out the satellites.
I think, Tony, well, well, he highlighted the fact that there is no one single instrument or one single system that is the solution. So it's the combined use of all this information that makes possible for a forecaster, that I'm sure that they are in the audience, to issue a warning. And this is the last mile, which is extremely important. It's not only providing, so it's the last mile, so the forecaster, they are the best integrators of all information we are providing.
And I understood something you did very nice at the WMO. You made a sort of kind of online museum. So you're already working for years how to do things digitally. I'll put the link into one of the question or a chat sessions later on celebration of the 20th anniversary. You made an online museum where you can switch into the future, what happens to the WMO. It's great. I will send it out. One last question. What is your dream for 2030?
I think that most of the people working in this field, they would like to see the data, our data, EUMETSAT data, but data from all the agencies, and to be used to not only to defend and to make the planet safer, but also to make our planet much better. And this is probably the best wish we would like to see from EUMETSAT perspective and from all satellite agencies around the world.
Well, thank you very much. That's a good dream. Thank you so far, Mr. Paolo Rutti. We're going to the next speaker, or someone who we have seen before in the video, which didn't work at first, but then did work at the short break we had, Mark Higgins. He's responsible for user training at EUMETSAT. And EUMETSAT provides training on its data, its products, and its services. And what Mark's like to do in his spare time, well, playing games, ride bicycles, and sew. Like sew, stitching was like, wow, that's
Stitching,
cool for a
sewing.
guy. How did you come up with that?
I, as with many people during the beginning of maybe the lockdowns, I started making masks for our family by sewing, and then graduated up to making clothing. So it's a new skill that I've learnt during the lockdown periods. Of course, being involved in training, learning is something also close to my heart.
I can imagine, yeah. Well, you also pre-recorded something about the world of satellites. So let's look at that. And then later on, we are starting with the questions.
The METOP second generation consists of 2 satellites working in tandem. The first of the satellites has 6 instruments on board, covering a range of environmental parameters and all looking at the same place on the Earth to give an integrated perspective. In particular, the A satellite offers really detailed information on the composition of the Earth's atmosphere. The second satellite hosts 4 instruments and the Argos data collection platform, which collects data from marine instruments around the world. The 4 main instruments give us information on the oceans, the atmosphere, and the clouds. Each instrument has its own scanning pattern and perspective. Some of the instruments give us vertical profile information of temperature and humidity, or of the chemical composition of the atmosphere. Some of the instruments are sensitive to the clouds, giving us information about the particle sizes or the distribution or the makeup of the clouds. Other instruments see through the clouds. Some of the instruments give us information about the surface of the land or the ocean. The data from the instruments can be used individually, or the information can be integrated to give us a full picture of the environmental system. The comprehensive data from these satellites feeds into the models used for forecasting the Earth system. And all of the data are used by science and research across Europe and the world.
So you can see in this video just how tremendously complicated the EPSSG, the second generation polar system, is. Now that video tells the whole story, but we're going to make available chunks of it. So if you, in your storytelling, would like to use some of these videos to explain the new observing system, you're very welcome. And all of that will be available on our website. So we're really hoping that people will be able to share and help people understand what the satellite system does. But one thing you can really see that I'd like to pick out from the second generation polar orbit satellite is just how all of these instruments work together. We saw this in Tony's presentation of the importance of there is no one satellite instrument that's king. And that's very, very true for the new missions of what we see together. These instruments working together. Now, Helga, just before we go on to the second video, I'm going to share something. My sister actually lives in the Netherlands, so it's hearing your voice and seeing you wearing orange. I'm feeling a little bit happy to remember her, but also really sad because I've not seen her for a whole year. So she lives in Wassenaar and works for the European Space Agency. But that's enough about me. Let's move on to the EUMETSAT third generation. So we have a video here that will show the EUMETSAT third generation configuration. And as was mentioned already, this is really focusing on nowcasting. So let's see that video.
The EUMETSAT third generation system consists of 3 satellites. EUMETSAT maintains these satellites so they have a continuous view of the Earth. The first of the satellites hosts the prime service, which is the imaging service. The instruments involved are the flexible combined imager, the lightning imager, and the data collection and search and rescue support platform. The flexible combined imager takes images of the Earth every 10 minutes in 16 different spectral channels. This gives us information of the clouds, their properties, as well as information on the land and water surfaces. The lightning imager consists of 4 different cameras, giving us information about lightning for the full disk, day and night. The MTG Imager service is used to provide support to nowcasting, forecasting immediate meteorological dangers. The second of the satellites in the MTG system provides the sounding services, taking vertical information of the atmosphere. There are 2 instruments, the infrared sounder and the ultraviolet visible and near infrared sounder. The infrared sounder, IRS, provides information on the temperature and humidity in the atmosphere. We get information for the full Earth disk, but we get information for Europe every 30 minutes. The Copernicus mission provides information about the composition of the atmosphere over Europe. This atmospheric composition information will be new information for weather services and other services around Europe. The third satellite in the constellation provides the rapid scanning service. It also hosts a backup of the lightning imager. Here we get images of Europe every 2.5 minutes. This is important for monitoring very rapidly evolving storms. All of the information for the MTG system is made available across Europe and the world and is used for weather forecasting through to atmospheric composition monitoring.
So that's the EUMETSAT third generation. And of course, it's the data that we're most excited about and what that's going to be able to do to support you in your roles. But just in the storytelling, we really hope that these short segments of video will be useful to you.
And where can we find those segments?
So we're going to make them available. They will be on the media section of the EUMETSAT website. What I'll do now is I'll just check to see if they're available already. And if they are, I'll post them in the chat.
Yeah, well, that's great. And in your partner section, because on the partner section, we also have all kind of links to watch. Maybe that's nice as well. What I was thinking, dear Mark, I know there are satellites sending out every minute, especially if it's going with thunder or whatever. When is EUMETSAT sending out every minute?
So we won't be at every minute. We'll be every 2.5 minutes. So as of about 2025, you'll have data available every 2.5 minutes. Now, there's a reason for that. The US system, where you can get this 1 minute data, they have a very focused grid that they can focus on 1 or 2 parts of the US to really see these small storms. Now in Europe, what we're having to do is cover a much wider area. So we've made the choice to cover a wider area, all of the European area, and we'll be doing it every 2.5 minutes. And you'll have all of those data from about 2025. And that'll include the lightning data as well, which I'm really excited about.
I'll keep you on to that. I'll keep a notice. 2025.
Do.
Mark, you promised me something back there in 2021. What are you curious about?
Yeah.
What we are able to visualize in the future?
I think one of the things I'm most excited about that sits inside the new programs is fire applications, both in the central parts of Europe and in the Nordic areas. I think there's a lot of the instruments that we'll be able to use that really help us look at the whole fire cycle. So from the ignition of fires, the weather that comes before fires, while they're burning, and also the burned areas afterwards that can be a risk for landslip. I think that's one of the areas I'm most excited about this. But just seeing what people do, the creative and innovative potential is just enormous.
We have got a bad job. We like the bad weather, which is also awful for the people. But we think, yeah, something's happening. Fire, thunder, storms. Yeah, okay. Well, thank you so much for your help. We're going to talk later to you in this program. I would like to announce Stephen Boyinski. Stephen has 17 years of work experience with weather and climate communities in the United Nations World Meteorological Organization, ESA and EUMETSAT, and he lives in Germany. As an expat, he grew up there and he returned 20 years later. A nice anecdote about Stephen, he threw a Swiss cheese and wine party after his probation period at EUMETSAT. That's a way to say hi to your colleagues. That's a good way. And some of your colleagues still recall that moment. Swiss cheese and wine parties, we love that. Well, what makes you happy? I asked him, and he says, well, summer after COVID-19, that will be great. And in spare time, he likes nature, he likes sports, and watching online live concerts. And what can I wake him up for in the middle of the night? Well, a project to change the world. Small is beautiful. Small is beautiful. I would like to learn more. Stephen, please explain us how EUMETSAT is preparing users to future generations of weather satellites and presenting the capabilities and impact on weather forecasting and nowcasting.
Yes, thank you. I'm happy to be here. Thank you for the introduction. In this presentation, I focus a bit more on the weather and nowcasting aspects of the new missions. My colleagues have previously talked about carbon cycle, about climate, and I'll touch on those things, but I'll focus on the weather component and what we can bring to the weather forecasting. So as has been mentioned already, we have basically these two eyes in space that allow us to know and to take the pulse of the planet, as we often say in the Earth observation community. So we have satellites in the geostationary orbit, which are 36,000 kilometers away. So they can see the whole Earth, but they're further away, so they can't see it as accurately as the instruments on the polar orbiting satellites, which are around 900 to about 1,300 kilometers away from the Earth's surface. They give us data which is critical for forecasting up to 10 days, whereas the geostationary data are really, really important for these nowcasts, which are forecasts up to about 6 hours. So those nowcasts are, if you will, a last line of defense. So the forecasts for 5 days, 3 days have been in, and they have been more or less accurate, as Tony McNally has been indicating. But then what is really happening in the last hours when weather systems can change quite rapidly, especially in convective systems and others. So we are planning these two highly innovative programs at the moment, and the METEOSAT third generation and the EUMETSAT Polar System 2nd generation. And I'm not going into the details of all the sensors because you've seen those in the videos just before. But what's written here are the launch dates of these various satellites. And we are very excited to looking forward to the launch of the MTG-I, which is the imaging satellite, end of next year. So that's here on the right, launch in late 2022. And then the others will follow suit. And there was a question about the 2.5 minute, 1 minute data. So the second MTG-I satellite here on the left, which will provide this rapid scan service, which is scanning the upper quarter of the Earth disk, including Europe, every 2.5 minutes. And that's due to launch in 2025, with data becoming available about 6 months later. The important message to everybody here in the audience that we are in here for a long haul. So we are really planning and committing to operate all these instruments for 20 years and more. So if you are investing now your intellectual brains, your capacity, your display systems into using this data, it is a good investment because it will reap benefits for 20 years and more. One of the key reasons to design this MTG, this METEOSAT 3rd generation, was to improve the prediction of high impact weather and that's of a concern because severe weather events such as hailstorms are becoming more frequent and intense in Europe and other places. This has been shown by the science and the observations. And so one really important application is to better characterize those big convective storms that form on typical summer days where there's sufficient temperature, humidity, and wind shear to be able to lead to convective developments, which then lead into thunderstorms. And so what I'm showing you in the next few slides are all these instruments that help us better characterize such severe storms and other things. So the imager, which will come on METEOSAT 3rd generation, there are two imagers. The one on the top here is the one that will scan the full Earth every 10 minutes. So it's Europe and Africa, the Atlantic Ocean, and parts of South America in 16 spectral channels. These are our eyes in the sky. We have not only 3 sensors on space that give us indication of what a human eye would see, but we have 16 eyes, if you will. The rapid scanning service at the bottom here comes on the second imaging satellite, which is due to be launched in 2025. And that will give us data again in these 16 spectral channels, but only for this upper quarter of the full disk, but then every 2.5 minutes. So that's really important to be close to what's happening in reality on the ground in the weather. So I mentioned this comparison with the human eye. So we have these 16 channels, and they are sensitive to various aspects of the atmosphere, to the clouds, to the presence of water vapor, to other things, to the surface, to ocean surface temperature, to land surface temperature, to radiation, and many other important meteorological phenomena. We use data that already exists from our colleagues in the United States to illustrate what the improvement compared to what we have currently from METEOSAT second generation is. So on the left here, you see data sampled as if we have it today over Europe. So that's the MSG, the METEOSAT 2nd generation, what you currently have. So at the top, you have this relatively coarse sampling of the weather every 15 minutes. And at the bottom, you have data for the same situation every 5 minutes. On the right, you have the improvement that we will see with METEOSAT 3rd generation. So on the top, every 10 minutes, the full disk scan. And at the bottom, you have almost a movie. You have every 2.5 minutes, you get a image, and that is quite close to a smooth movie. We don't have a video camera in space yet that is able to do all the things we'd like to do, but we have imagery every 2.5 minutes. There's also many other improvements coming with MTG, and this is a much higher definition, much higher resolution, and much clearer and brilliant imagery, which is not only important for weather forecasters and situational awareness, but also for media and outreach purposes. So on the left, you have what we currently can see with our imager in geostationary. And on the right, it's data from an existing mission, but it's mimicking what we will see from the next generation imager. So you can see much more clearly the cloud patterns. You see land surface features, vegetation features. You also see the ash plume from the Etna volcano on Sicily. You see features in the ocean color features. So you see many things that you don't see on the left. Another important application, it's less to do with climate and climate change, but it's really, really important if you fly planes. So you want to know, is it going to be foggy in the airport or in the flight route or not? And this is what we can currently see, seen over the Balkans, and this is what we will be able to see. So it's a much clearer depiction of the distribution of low-level clouds and fog, which is very important to many of our key users. Now, coming to the lightning imagery mission, so there are lightning detection networks on the ground which are used every day by weather services for forecasting. What's new here is that the lightning imager will continuously stare at the full disk, including Europe, and will measure signals that come from lightning. So on the right here, this is a simulation of what we expect to see from this geostationary lightning imager. So for a very convective day over Central Europe and France, so you see a representation of lightning density here. So if the color is red, it's more dense than if it's yellow. And this adds information for forecasters, because if a storm intensifies, it's usually jumping its lightning activity. So it's the first time we are able to monitor total lightning activity from space. And because we are all very visual people, I thought I show real data that has been acquired from a similar instrument that's flown by our colleagues in the United States, of a massive connective line over the continental United States with lots of lightning in it. So the data that we will get from our MTG lightning imager will look something like this. We don't usually have storms this large over Europe, but it gives you an impression on what the data will look like. And I know that many weather services are currently experimenting how to most effectively display data from the lightning imager in their forecasting, and also for media and outreach. Now, the third sensor that we are really excited about is this infrared sounder, which is the first time we have continuous profiling of the atmospheric state over Europe and Africa. We have instruments currently flying on the polar orbiters, but they only see every place on the Earth once or twice a day, whereas this system is going to scan the temperature and moisture field every 30 minutes. And we expect this to be a real game changer for nowcasting severe weather, but also for longer range forecasting of weather. Now we have all the components, we think, that we need with observations and to inform the models about the convective cycle, and we'll expect many more applications of this data. I'm anticipating the future a little bit with this animation, where we show the co-location of all this information in one place. So we call it the 4D weather cube, the 4-dimensional weather cube. So it's continuous scanning of and tracking of atmospheric dynamics over time, over places in Europe. And this will lead to hopefully improved forecasting, but it's also a challenge for the whole visualization and software display software community, because we need to find effective ways to display this data. We don't have the single solution at EUMETSAT yet, so we're working with the Met services and others, software companies, to find good ideas on how to visualize this data most effectively. Now, I'd like to have one slide on climate. So all this data is obviously informing climate monitoring and the things we'd like to know about climate development. So we have on the top here this time line, and we have data from METEOSAT satellites now for 30 years, and we can commit to continue creating climate data records, which means data sets that allow us to say something about climate variability and trend with a known uncertainty over time. One important feature is, for example, that if you look at the peak intensity of tropical cyclones in the Atlantic and you take the northern hemisphere, then if you take the peak intensity and you look at what latitude that peak intensity occurs, that latitude has been increasing over the past 20 years, which has been possible with satellite data. This means, in short, the stronger storms are moving north and are providing a threat to areas which before have not been threatened by strong tropical cyclones in the past. There are many other pieces of information that will be provided by EUMETSAT third generation for climate monitoring. So I'm summarizing all the applications that we see with MTG. We mentioned weather forecasting, I mentioned fog detection, lightning monitoring. I didn't talk about air quality monitoring so much. There is a very important instrument on this satellite, which is funded by the European Commission Copernicus program, Sentinel-4, which will provide unprecedented snapshots of air quality over Europe. Fire detection and monitoring is going to be very important, as Mark mentioned, enhancing numerical weather prediction. Let me just summarize in this slide what we expect the contribution from the second generation polar orbiting METOP satellites will be. Tony McNally alluded to this in his presentation. There are many different observing systems that contribute to the reduction of errors in weather forecasts. Satellites have a major component here, and if we just take the EUMETSAT METOP satellites, they contribute to about half of the reduction in errors in forecasts. And we expect with the second generation satellites that this contribution will increase. Just one more slide on the polar orbiters and how they can support nowcasting. We have here an example where we had 3 consecutive overpasses within a bit more than 1 hour over Scandinavia, capturing the evolution of a severe convective line. These events are becoming more frequent over the past 10-20 years in those latitudes. This also speaks to the needs of Iceland, for example, which was mentioned before. And so in these images, you see how this little system is evolving. And that's really important in areas where there's no other observations. So I'm just summarizing what we expect, in which applications we expect the second generation polar orbiters to be useful. And with that, I'd like to finish my presentation. Stay future focused. Thank you.
Thank you, Stephen. You can now switch on your camera because we see a very nice image of you, a still picture, but I see you talking. So maybe you can work on the camera. And for the people who can't see the images in the big screen, I saw there were some issues. We have an official program from Swapcard, but well, hey, things might go a little bit wrong sometimes. So refresh. If you refresh your page, then everything will go back in the modus it should be. So try that, and then you can go again back to the chat and to the questions. I saw it wasn't possible to get in, but if you refresh, you get in. And something else, all the presentations will be recorded. So if you weren't able to follow it now, or you want to recall it later, it's fine. Tomorrow, today will be posted. That's a good one. Tomorrow you can find the videos of today back somewhere in the system. We will tell you about that tomorrow. So far. One more question to Stephen. Stephen, what's your dream for 2030?
My vision for 2030?
Your vision or your dream, or both?
Yes. I'm hearing another voice. Yes.
You hear me? What's your dream for 2030?
Well, my camera is on. I can see myself in Teams.
Yeah, I can see you as well. No, I still see your nice picture, but just tell us, let the camera go. Just tell us, what is your dream for 2030?
I'm fascinated by actionable information. So I work a lot at this interface between science, policy, and society. And I'm a scientist myself, but haven't done science in a long time because I moved into this interfacing role. And I see the power of science when it's communicated well by relatively simple, but not too simple indicators. And this, you know, this idea of having a carbon weather in 10 years, or having a real-time assessment of what's the impact of my behavior in an app or some other application. I think that's my vision.
Well, that would be great, because all the weather presenters watching are looking for almost real-time information, and also climate information. The sooner they get on when the event happens, the better it is to explain to the people and to the audience. So there's a big issue for you ahead.
Yeah.
Thank you so much. If there's still questions for him, for Stefan, or any other person, just put it into the question map, and I'll ask all the speakers to search into the maps if there's still answers to be answered, questions to be answered. All right, this will end up the first part of the Future Focused. I can imagine that all the time behind the computer is like, oh, I need to stretch, I need to drink, I need to pee, I need to do something else. We have a little break and we will start back at 11:35. In the meanwhile, discover a swap card. There's a coffee lounge section. Go to the partner areas, fill in the satisfaction surveys, if you like it or not. 11:35. I'll be back, and you too, I hope. See you later.